If you've ever wondered why Bitcoin was the first e-cash to succeed at decentralized payments, then this video is for you. Bitcoin was made possible because its founder, Satoshi Nakamoto, was able to solve for the Byzantine Generals Problem. Today, we're diving into what that is and how he solved for it. The Byzantine Generals Problem is a foundational issue in distributed computing and game theory that highlights the difficulty of achieving consensus in systems where participants can't rely on trusting each other. The problem was first introduced in 1982 by Leslie Lamport, Robert Shostak, and Marshall Pease. They posed a question that has since become the cornerstone of how we understand decentralized networks like blockchain. The question is this: how can a group of people, each potentially unreliable, separated by great distance, lacking dependable means of communication, or even malicious, come to an agreement without a trusted central authority? In the case of Bitcoin, Satoshi solved for this with a workaround called proof of work. But more on that later. The question of decentralized trust is usually illustrated with a fictional story. Several Byzantine generals surround an enemy city. To succeed, they must coordinate an attack. If they all attack at the same time, they win. If one of them attacks while the others do not, they lose. The challenge is that these generals can only communicate via messengers, and those messengers might be intercepted, delayed, tampered with. Even worse, some of the generals themselves might be traitors and intentionally try to mislead the others. The question becomes, how can loyal leaders agree on a plan when the reliability of both their communication and each other is uncertain? This problem might seem abstract or historical, but it's deeply relevant to digital systems, especially decentralized ones like Bitcoin. In a distributed computer network, nodes act like generals. They need to agree on the state of the system, things like the order of transactions or the validity of the data, without being able to trust each other. Centralized systems don't face this issue in the same way because a single authority decides what's true. For example, in banking, a central bank or financial institution tells everyone what the balances are. If they're compromised, though, the whole system fails. So rather than solving the Byzantine Generals Problem, centralized systems simply sidestep it by creating a single point of trust and a single point of failure. In decentralized systems, the Byzantine Generals Problem must be solved directly. The concept of Byzantine fault tolerance emerged as a way to describe systems that can continue operating correctly even if some participants fail or act maliciously. A Byzantine fault-tolerant system can handle some portion of its components behaving unpredictably or dishonestly and still reach consensus. Bitcoin is perhaps the most well-known real-world example of a Byzantine fault-tolerant system. While Bitcoin doesn't solve the Byzantine Generals Problem in a purely theoretical sense, it does offer a practical working solution. Satoshi Nakamoto didn't find a generalized mathematical solution that solves the problem, but he built a system that works anyway. Satoshi's key insight was to combine several ideas: game theory, public key cryptography, distributed networking, and proof of work into a system where participants don't need to trust each other. In a forum post from 2008, Satoshi Nakamoto described the proof of work chain as a solution to the synchronization problem that verifies every transaction and block according to a predefined set of consensus rules. There is no central authority. If a miner proposes a block that breaks the rules, the rest of the network ignores it. All nodes maintain their own copy of the blockchain and agree on which version is valid based on these shared rules and the amount of computational effort embedded in it. Bitcoin has proven to be extremely resilient. Even if some miners or nodes act maliciously, the network continues operating as long as a majority follow the rules. The financial incentive structure of Bitcoin also encourages good behavior. Miners spend real resources to compete for rewards in the form of new Bitcoin. If they try to cheat, their blocks are rejected and they lose money. This is game theory in action. Rational participants are incentivized to cooperate with the network's rules because doing so maximizes their profit. Bitcoin also elegantly handles the double spending problem, which is another way of framing the Byzantine Generals Problem in the context of money. If two transactions try to spend the same coin at the same time, which one is valid? In a centralized system, a bank decides. In Bitcoin, the longest, or rather the heaviest, valid chain wins. Once a transaction is included in a block and that block is confirmed with additional blocks added on top of it, reversing the transaction becomes effectively irreversible due to the network's consensus mechanism. Bitcoin's solution isn't perfect. It remains vulnerable in theory to a 51% attack. If one entity controls a majority of the network's computational power, it could rewrite history. But this is prohibitively expensive at Bitcoin's current scale, which adds a layer of economic security. Satoshi's design fundamentally changed the way that we think about trust in digital systems. By removing the need for a central coordinator and making consensus possible even in the presence of malicious actors, Bitcoin created the first decentralized monetary system that can resist manipulation and censorship. The Byzantine Generals Problem illustrates why it's hard for decentralized actors to agree on a shared truth. Bitcoin doesn't solve it in a purely mathematical sense, but it works. It sidesteps the need for trust through proof of work and open source verifiable consensus rules. Every node in the Bitcoin network is a general, but instead of trusting each other, they independently verify every move. That's the brilliance of Satoshi's design. Not a perfect solution, but a practical one that works in the real world. If you enjoyed this video, give us a follow and be sure to head over to bitgo.com to learn more.